We have started to deal with the problems of microcanonical ensemble in the previous lecture. In this regard, today we are going to see a very important problem of this microcanonical ensemble, and actually in this problem we are going to derive a very important and very famous formula which is called Sackur-Tetrode formula or Sackur-Tetrode equation. Actually, what is this Sackur-Tetrode equation? You know that Sackur-Tetrode equation is simply the expression for entropy of a perfect gas in macrocanonical ensemble. So this question may be asked in this way too, that derive the expression for entropy of a perfect gas in microcanonical ensemble. Okay. So the heading which I have written, Sackur-Tetrode formula, means expression for entropy of a perfect gas in microcanonical ensemble. Okay. Actually, in the previous lecture you have seen a general expression for finding the entropy of a system in a statistical mechanics, and actually we will utilize that result which we have learned in the previous lecture in this lecture. So as we have to find entropy of a perfect gas in microcanonical ensemble, so for this let us consider a microcanonical ensemble of a perfect gas, and we consider that this ensemble consists of n particles and each particle has a mass m, and these are confined in a volume V, and at the same time the total energy of this system lies in the interval between E minus delta E and E. It means in interval delta E the energy of this system lies. Okay. You have learnt in the previous lecture that in this energy range, if you want to find the accessible volume or accessible region in phase space, what will be that? You know, you have learnt earlier that this volume is given by the product of delta Q and delta P, and this is actually equal to integral of summation I1 to n. This is product of dqi times dpi. Okay. You have seen this result several times earlier, so there is no need to explain this. Now, just in the previous lecture, we have learnt that when we divide this volume in phase space delta Q times delta P by h to the power f, where h is Planck's constant and f is degree of freedom of the system, then we get the corresponding number of quantum states. It means what is the number of quantum states in this much phase in this much volume of phase space, that can be obtained simply dividing this volume in phase space by h to the power f. Here we have considered that the total number of particles in this system is n, so the degree of freedom will be equal to 3n, because each particle will have 3 degree of freedom and number of particle is 3, so the total number of degree of freedom will be 3n. So when we will divide this expression delta Q times delta P by h to the power 3n, you will get the number of quantum states corresponding to this volume in phase space, and we denote this number of quantum states by the symbol delta gamma as we have used in the previous lecture. So delta gamma will be equal to what? This is 1 over h to the power 3n integral pi I to n dqi dpi. Okay. Now our aim is now to evaluate this integral, but actually you know that the system is made up of perfect gas, and the molecules of perfect gas, you know, are non-interacting. That it means there is no interaction between the molecules or particles of a perfect gas. And as you know, if there is an interaction between the particles of a system, due to that interaction, potential energy is developed in the system. So the potential energy is also called energy of interaction. But since our system is of perfect gas and its molecules are non-interacting, so there will be no potential energy in this system. So you can say that potential energy V of this system will be 0. Why? Because there is no interaction between the particles of this system. Okay. And as potential energy is 0, so when you will talk about the total energy of the system, that will mean simply kinetic energy, because you know that total energy E is equal to kinetic energy plus potential energy. But since potential energy is 0 in this case, so total energy means simply kinetic energy. Okay. And what will be this kinetic energy? You know, if we consider an ith particle, its kinetic energy will be equal to pi square divided by 2m. Okay. Here pi is the momentum of the ith particle, and when you will sum up this kinetic energy of all particles, you will get the total kinetic energy, and that will be equal to the total energy. So the energy of this system is simply equal to kinetic energy. I have mentioned it here, and this will be equal to summation over I1 to n pi square divided by 2m. Since mass of each and every particle is same, so I have not written here mi, because m is same for all particles. Okay. Now you can see that this expression for energy is independent of positions of the particle. Okay. So in this condition, when we see the integral in this integral pi I1 to n dqi, what will be this? Actually, this is total volume in position space. Total volume in position space. And the volume associated with each particle will be equal to V. So this integral means you have to multiply this V n times, that is V into V up to n terms. So when V will be multiplied n times, this will be simply V to the power n. So the volume in position space, which is given by this integral, that will be simply equal to V to the power n. And so from this equation you can see from equation 1, the integral of product of dqi, that will be V to the power n. So equation 1 now becomes like this. This is delta gamma equal to V to the power n divided by h to the power 3n times integral pi I1 to n dpi. Okay. Now our problem is to evaluate this integral in which is actually the volume in fact in momentum space. How we will actually evaluate this? Actually, you know that we have considered the energy of this system lies in the interval delta E, that is, it lies between E minus delta E and E. Okay. And we have calculated that the energy of the system E is equal to this much. So you can say that this momentum space integral in this equation 2 can be evaluated under the condition that E minus delta E is less or equal to summation over I1 to n pi square by 2m, and this is less or equal to E. Under this constraint, under this condition, you can evaluate this momentum space integral. Okay. And for evaluating this integral, now let us think about a three-dimensional sphere, and we consider that if energy is equal to E, let us say momentum is P. Okay, momentum is P. And what will be this momentum P in terms of E? You know that P square divided by 2m is equal to E. And so you can say that this P is equal to 2me. P is equal to 2me. Okay. And corresponding to this energy E minus delta E. E minus delta E. We will write that the momentum will be equal to root over 2m E minus delta E. So in momentum space, we will consider two spheres. The inner sphere has a radius equal to 2m square root of 2me, and the outer radius and the outer sphere has the radius square root of 2m E minus delta E to the power half. Okay. So actually, when you talk about this volume in momentum space integral, that will mean the volume between these two spheres, but in 3n dimensional space, not 3D space, but between in 3n dimensional space, the volume enclosed between these two spheres having radii equal to root 2me and root 2m times E minus delta E, that will be the volume which is equal to this integral. Okay. Or you can say that this integral represents the hypervolume between these two spheres or spherical cells. Okay. But how we can find this volume of hypersphere having a radii between this square root of 2me and square root of 2m E minus delta E. Okay. Actually, we will find this volume with the analogy of the two spheres of same radii in 3D space. If you consider that our space is 3-dimensional, then what will be the volume? Actually, we will subtract the volume of this inner sphere from the volume of the outer sphere. Okay? Volume of the outer sphere. And what will be the volume of outer sphere? You know that volume of a sphere is given by 4 by 3 pi r cube. This is the formula for volume of a sphere. So the volume of the outer sphere will be 4 by 3 pi square root 4 by 3 pi r cube, and r is actually equal to, sorry, here I have actually mentioned it wrongly. This should be equal to this much, and this larger sphere is this, because here I have written E minus delta E. Sorry, you should mark it that the inner radius is this much and outer radius is a square root of 2me. Okay. So when you will subtract the volume of the inner sphere from outer sphere, you will get the volume between these two spheres, and that will be 4 by 3 pi. And when you will cube this 2 square root of 2me, this will be 2me to the power 3 by 2. Okay, and minus this much. So this is the volume of a three-dimensional volume of a hypercell having inner radius this much and outer radius this much. Okay. Now let us simplify this result to some extent. Actually, this factor 4 by 3 pi can be put in a particular form. In terms of gamma function, we can write this number 4 by 3 pi in this way. This is pi to the power 3 by 2 divided by gamma 3 by 2 plus 1. You can check when we will actually put the value of this gamma function and evaluate this number, that number will be same as equal to 4 by 3 pi. Okay, so you should remember it. But you know that gamma n plus 1 is equal to simply factorial n. So this gamma 3 by 2 plus 1, this will be factorial 3 by 2. Okay. So this integral, that is integral of dp, means the volume in three-dimensional space of a hypercell of radii this much and this much. Okay. And so this is equal to pi to the power 3 by 2 over 3 by 2 factorial times 2me to the power 3 by 2 minus 2me minus delta e to the power 3 by 2. So getting an analogy from this three-dimensional space, you can now find what will be the value of this integral. Actually here only the dimension of space changes. Radii remains same, but dimension of space changes. So you can think in this final result that this number 3 actually represents the dimension of the space. 3 represents dimension of space. So when we will find the volume between these two spheres in 3n dimensional hyperspace, 3n dimensional space, then in this last result only this 3 will be replaced by 3n, because the number 3 comes from the dimension of space. So this integral, which represents the volume between radii square root of 2me and square root of 2me minus delta e of 3n dimensional hypersphere, what will be that? Only you have to replace this 3 by 3n. In examination, this discussion is not necessary. You can remember this result as a formula. As you know, volume of a sphere is 4 by 3 pi r cube, and you remember it. Just like that, you can remember that formula. Okay. And so you can see what is this volume. This integral pi I1 to n dpi, this is equal to what? You can see I have only replaced 3 by 3n. So this is pi to the power 3n by 2 divided by 3n by 2 factorial times 2me to the power 3n by 2 minus 2m times e minus delta e whole to the power 3n by 2. Only what is the difference? Difference is only what? Instead of 3 dimension, now the dimension of a space is 3n. So 3 has been replaced by 3n. Okay. Now we will simplify this result. You can see, you can take this 2me to the power 3n by 2 as a common factor. Actually in this second term 2, this factor is present. This is 2me, 2m, when you will multiply this 2m by e, this will be 2me minus 2m delta e. Okay. And whole to the power 3n by 2. So this 2me whole to the power 3n by 2 has been taken as a common factor. So at the place of first term only 1 remains here, and in the second term instead of this 2me I have written 1, and since e is not present in the second term, so you have to divide this delta e by e. Okay. So you can see this. Okay. Now you know that when 1 minus x to the power n, when it is expanded, and when e to the power minus x is expanded, result is same. E to the power x, you know, this is 1 minus x plus x square by 2 factorial minus x cube by 3 factorial. Okay. And when you will make the binomial expansion of this 1 minus x to the power n, the result will be again same. E to the power nx, not x, sorry, nx, e to the power minus nx. So here will be n, here will be actually n into n minus 1, here will be n into n minus 1 into n minus 2. Okay. Have you understand or not? When 1 minus x to the power n, this will be simplified by binomial expansion. What will be the result? This is 1 minus nx plus n into n minus 1 by 2 factorial x square minus 1. And similarly, this e to the power minus nx is also like that. So this 1 minus delta e by e whole to the power 3n by 2, this can be written as e to the power minus 3n by 2 into delta e by e. Okay? Have you understand? Now, in any statistical system, you know the number of particles is very large. It is of the order of 10 to the power 28, 10 to the power 23, okay, 10 to the power 30. So in this equation 2, this n will be very large, and as exponential has negative power and n is present in its power, so this exponential factor will be very small. This will be very small. And so we can neglect this exponential term in comparison to 1. Okay? So this exponential has been omitted from here and neglected, and your result is what? Your result will be then, this is pi to the power 3n by 2 divided by 3n by 2 factorial times 2me to the power 3n by 2. I have mentioned it here. You can see n is large. So this exponential factor is much smaller than 1. And so this has been neglected in comparison to 1. I think you have understand. Okay. So finally, we have obtained the value of this momentum space integral. And after getting this value, now we will substitute this value in equation in this equation number 2. Okay. So what will be now the number of quantum states delta gamma? You can see this will be v to the power n divided by h to the power 3n times this momentum space integral, and we will substitute the value of this momentum space integral which we have obtained in this equation 3. So you can see this delta gamma is now v to the power n divided by h to the power 3n times 3n by 2 factorial times 2 pi me to the power 3n by 2. Actually, I have included here pi with 2me because pi has also power 3n by 2. Okay. And this expression can be written like this. This is v to the power n divided by 3n by 2 factorial. And instead of this h to the power 3n, I have written here, you can see, h square and whole to the power 3n by 2. So this 2 and 2 will cancel out and h will contain 3n power. So the result is same. So finally we get the number of quantum states in the accessible region of the phase space is equal to what? This is v to the power n divided by 3n by 2 factorial times 2 pi me over h square whole to the power 3n by 2. Now, after getting the value of number of quantum states corresponding to the volume delta q times delta p in phase space, now we can easily find what will be the entropy of the system. What will be the entropy of system? Because in the just previous lecture, you have learnt that the thermodynamical entropy of a system is given like this. This is k times log delta gamma. You can remember, just in the previous lecture we have learnt this. Here k, you know, is the Boltzmann constant. Now we will substitute this value of delta gamma which we have obtained in equation 4 here. So S will be what? S is k log this much. This is actually the value of delta gamma as you can see in this equation 4. Okay. Now this factor 3n over 2 factorial is in the denominator. So we can simplify this result to some extent. Here v to the log v to the power n, you know this can be written as n log v. So using the property of logarithm, you can see that s will be equal to nk log v times 2 pi me over h square whole to the power 3 by 2. Actually here n, the power n has been taken in multiplication, because you know that log a to the power n is equal to n log a. Okay, using this property of logarithm, we have written like this. Okay, and since log a divided by log b is log a minus log b, so this will be minus k log 3n by 2 factorial. Okay, k is a common factor. Now this last term, which contains log 3n by 2 factorial, you know from Stirling approximation that log x factorial is equal to what? This is x log x minus x. So using this Stirling approximation, you can write this last term in this manner. This is k times 3n by 2 log 3n by 2 minus 3n by 2. At the place of x, there is 3n by 2. Okay. So s becomes like this. Now we will again try to simplify this result to some extent more. So you can see that this should be here. See here, this is nk log v times 2 pi me whole divided by h square to the power 3 by 2, and see this now the last term is simplified like this. We will multiply, we will take this n as a common factor, so this will be nk log 3n by 2 whole to the power 3 by 2, because n has been taken as a common factor. Okay, and plus 3 by 2 nk. Okay, 3 by 2 nk. So actually this bracket should be here, this bracket. There is no need of this bracket here, because the last term has been simplified. Okay. Now in the first two term, logarithmic term, you can see this nk is a common factor, so take this nk as a common factor. Okay, and you know log a minus log b is log a by b. At the place of a, there is in fact v times this much, and at the place of b, there is 3n by 2 to the power 3 by 2. So the first two terms can be coined like this. This is nk log v times 2 pi me divided by h square whole to the power 3 by 2 and divided by 3n by 2 whole to the power 3 by 2. And the last term remains at it. You can see this is 3 by 2 nk. Okay, and we actually write this expression in a particular manner. You can see s will be equal to nk log v times e divided by n to the power 3 by 2. Here you can see there is e, and e contains power 3 by 2, and in denominator there is n, and it has also power 3 by 2. So you can write e by n to the power 3 by 2. And what is the remaining factor? Remaining factor is 4 pi m, because this 2 will be in numerator now, divided by 3h square whole to the power 3 by 2. So this is the expression for entropy which we have obtained by considering the microcanonical ensemble made up of a perfect gas. Although no property of the perfect gas has been used here, only except that the particles are non-interacting and its energy is equal to kinetic energy. But now we will see, is this expression for entropy correct? You will see that actually this expression for entropy of a perfect gas is not correct. It is faulty. Because you know, entropy has a particular property. Entropy is an extensive property of a system, and due to its, as it is an extensive property, so you know that it is an additive quantity. You have learned all this fact in the previous lecture. When you say that entropy is an additive quantity, what does it mean? It means when we combine the two isolated systems, the resulting entropy becomes sum of the entropies of the individual systems. Okay? So we will try to see that this result obtained for the entropy satisfies the additive property of entropy or not. You will see that this does not satisfy the property of the additive property of entropy. So this result is faulty. So we will check it. So I have mentioned here that expression A1 is faulty. It is not correct. But how it is not correct, we will now check it. Now let us consider. We consider alpha number of identical systems. That is first system, second system, so on, alpha system. There are alpha systems, each are identical, every one is identical, and each contains n particles. Okay, each has volume V, okay, and energy E. So you can say that the entropy of each and every will be equal. So if entropy of first system is S, then entropy of second will be also S, and this alpha will also S. So according to the additive property of entropy, when all these alpha systems will combine, then the resulting intensity will be what? This will be S plus S plus S up to alpha terms. That is alpha into S. So if this result is correct, then according to the additive property of entropy, when we will combine alpha identical systems, each having entropy S, then the resulting entropy or the entropy of the composite system must be equal to alpha into S, alpha times of S. But you will see, surprisingly, that the result is not so. When we will combine all these systems, there will be an increase in entropy. You will see here what I have told. When we combine all these systems, n, you know that this V will increase by n, okay, E will also increase by n, okay. So at the place of the new entropy will be what? At the place of n, now we will write alpha n, because alpha systems has been combined and each system contains n particles. So the total number of particles is now alpha into n. V also becomes alpha into V. Energy also becomes alpha into E. So at the place of E, I have written here alpha E. At the place of n, I have written here alpha n. Okay. And in the last term too, you can see instead of n, I have written alpha n. Okay. Now let us simplify the RHS of this equation. Actually here this alpha is in the as a common factor here, and alpha is also present in the last term. So let us take this alpha as a common factor. Then what will be your result? This will be nk log V times e to the power n whole to the power 3 by 2. Here alpha and alpha will cancel out. What will be this alpha? We will see later on. And 4 pi m divided by 3h square whole to the power 3 by 2 plus 3 by 2 nk. But I have not considered this alpha, because you know log a into log b is log a plus b. So we can now write what? This alpha nk log alpha here. Have you understand? Because log A into log B equal to log A plus log B equal to log A into B. Okay. Now see the expression inside this square bracket. When you see this expression, you can compare this result with equation A1. This is nothing, this is simply S, that is entropy of one system. So instead of the expression inside this square bracket, now we will write S. So S dashed is equal to alpha into S and plus alpha and K log alpha. But what I have told you, if the expression for entropy you obtained here will be correct, then after mixing alpha identical systems, each having entropy S, in accordance with the additive property of entropy, the resulting entropy should be only alpha into S. But here we see, after using the expression obtained in here, you find that the new entropy of the combined system is not alpha into S, but it is greater than alpha into S by this much, alpha and K log alpha. So entropy of the system has been increased by this much. This is actually unaccountable entropy. From where it comes, no one can say. Okay. Actually, this phenomenon is the famous phenomenon which is known as Gibbs paradox. And we have studied Gibbs paradox earlier in my videos. So if you have not watched those videos on Gibbs paradox, definitely you should watch. You will see a detailed discussion on Gibbs paradox. So this is not a new thing for you. I have already discussed this thing. Okay. Although in calculation here again this Gibbs paradox has appeared here, but it does not mean that this is new thing for you, because you have learnt it earlier. Okay. So but why this extra term comes here, why this unaccountable entropy appears here? Something is wrong in our calculation. Actually we have applied the classical concept, and in classical concept actually the particles are assumed identical but distinguishable. Particles are assumed identical but distinguishable. When we will actually consider that the molecules of a perfect gas are distinguishable, then you cannot get the correct result. Actually, Gibbs has proposed this idea that you have to consider that the molecules or the particles of a perfect gas are not indistinguishable. Not distinguishable, but they are indistinguishable. This is quantum mechanical statistics. In classical statistics, particles are assumed to be distinguishable. But when you will consider distinguishability of particle, you will get the incorrect result. So to get the correct result, Gibbs introduced the idea of indistinguishability of the particles of a perfect gas. And when we will consider that the particles or molecules of the perfect gas are indistinguishable, then the number of quantum states which we have calculated by considering that the particles are distinguishable, that will get changed. The value obtained for this delta gamma, which we have learnt earlier, was based on the fact that the particles are distinguishable. But now we are saying that particles are not distinguishable. In that condition, actually we have counted some more permutation, more number of ways of distribution. Actually, when we will consider that the molecules are not distinguishable, then we will have to subtract the incorrect, or you can say the meaningless permutations from the value of this delta gamma. And for this Actually, this n factorial represents the meaningless permutations when we consider that the particles are indistinguishable. So the correct value of number of quantum states will be delta gamma divided by n factorial. To get the correct value of this number of quantum states, you have to subtract the meaningless permutations, and that meaningless permutation will be n factorial, because when one particle will replace another and particles are indistinguishable, no new states will be created, and so there are n factorial meaningless permutations in the calculation of this thermodynamic probability or this number of quantum states. So the correct value of the number of quantum states is given by delta gamma divided by n factorial. Okay, and this fact I have also discussed in very detail in Gibbs paradox, so you can watch those videos too to clarify your concept. So if you want to now get the correct expression for entropy, you have to write delta gamma over n factorial at the place of delta gamma in the expression for entropy. And so now we will write the expression for entropy like this. This is k log delta gamma by n factorial, not only delta gamma. And so you can see this will be k log delta gamma minus k log n factorial. Now again, this n log n factorial will be expanded by a Stirling formula, and when you will expand it in a Stirling formula, what will be this? This will be n log n minus n. Okay, so your result for S will be now k log delta gamma minus nk log n plus nk. Okay, plus nk. But you know, we have obtained the expression for this S earlier, only taking that this S is equal to k log delta gamma. You have calculated. So the value obtained for S earlier was only the value of k log delta gamma. So write that value here. I have written for k log delta gamma this expression which we have already obtained. Okay, up to this much. Okay, and the remaining terms you can see is minus lkn nk ln n plus nk. So these are the two remaining terms. Okay, now we will simplify this result. You can see that this 3 by 2 nk and nk, this will be 5 by 2 nk. Now this logarithmic term will be combined with this logarithmic term. Nk is a common factor, so take this as a common factor. Then there will be log this much minus log n, but log a minus log b, this is log a by b, so you can write this as nk log b by n, here n has been divided, okay, times e by n to the power 3 by 2 times 4 pi m whole to the power 3 by 2 plus 5 by 2 nk. Actually this is the correct expression for the entropy of a system. This is the correct expression, okay, because here you can see there is v by n. So when you will increase v by alpha times and n by also alpha times, the value of this alpha v by alpha n will remain same. This will be again v by n, and so the entropy will then satisfy the property of additiveness. Okay, so this expression is the correct expression for entropy, and you should remember it. Now we again use a very important property for perfect gas here, as E represents the total energy of a perfect gas, and you know if the number of molecules in a perfect gas at temperature T is n, then its energy is given by 3 by 2 nkt. This is a famous result, and we have used this in the statistical mechanics several times before. So E by n will be equal to 3 by 2 kt. So instead of this E by N, we will write now 3 by 2 kT. And then your equation A2 will become like this. This is S equal to Nk log V by N times 2 pi m kT over H square whole to the power 3 by 2 plus 5 by 2 Nk. Actually, this final result, which I have written here inside this rectangle, this is known as Sackur-Tetrode formula or Sackur-Tetrode equation. And this is actually the expression for entropy of a perfect gas in microcanonical ensemble. Okay. But we also write this Sackur-Tetrode formula in terms of another parameter which is called de-Broglie thermal wavelength. So now we will try to write this Sackur-Tetrode formula in terms of thermal de-Broglie wavelength. Okay. You know that the de-Broglie wavelength associated with a particle or molecule of a gas is given by H divided by average thermal momentum of the particle. Okay. And the average thermal momentum of the particle, this is given by 2 pi m kT whole to the power half. This is the expression for average thermal momentum of the particle. So de-Broglie wavelength lambda is equal to H over 2 pi m kT whole to the power half. And as in our expression for entropy, here in equation A3, you can see the factor 2 pi m kT whole to the power 3 by 2 is present. So from here we can calculate 2 pi m kT whole to the power 3 by 2. This will be what? This will be H by lambda whole to the power 3. So now we will substitute H over lambda to the power 3 instead of this factor 2 pi m kT whole to the power 3 by 2 in the final result. And after substituting this, you will see that this H square will cancel out and your result will be S equal to Nk log V by N times 1 by lambda cube plus 5 by 2 Nk. So this is the expression for entropy of a perfect gas in terms of the de-Broglie thermal wavelength. Okay. Or you can say that this is another form of Sackur-Tetrode equation. Actually, till now we have find the expression for S, and you know the symbol S represents the thermodynamical entropy. But in statistical mechanics, we also talk about a statistical entropy, and that is denoted by the symbol sigma. And you know this S is equal to K times sigma. And so sigma is equal to S by K. Okay. So if your aim is to find the expression for sigma, you have only to drop out K. This K will be omitted, and you will get then sigma. And again, you have also learnt earlier that the thermodynamic temperature is denoted by the symbol tau, and this tau is actually equal to K times, this is a statistical temperature, not thermodynamical. The statistical temperature tau is equal to K times T, where T is thermodynamical temperature. So if you also want to use a statistical temperature tau instead of T, you should replace this KT by tau. Okay. So for example, if you want to write this formula, let us say the formula obtained in this equation A2, in equation A3 for sigma, what you will do? We will drop this K, so there will be only N here, and instead of this KT we will write tau. Okay. And so the statistical entropy sigma is given by N log V by N 2 pi m tau over H bar squared to the power 3 by 2 plus 5 by 2 N. Here again K will be omitted. Okay. K will not present here. Okay. and this is the expression for the statistical entropy. Okay, so I hope you have clearly understand these calculations, because I have dealt the calculations in very detail, because this question is invariably asked in your university examination, and in competitive examination you have an idea of this, and then you can solve the objective question based on this. So thank you very much.